One more topic to talk about is the idea of symmetry in graphs. So our definition here, a graph is symmetric with respect to the y-axis. If whenever a point x comma y is on the graph, negative x comma y is also on the graph. By the way, just that WRT right there, that's Matthew abbreviation for with respect to. I'll use that a lot throughout the semester. A graph is symmetric with respect to the x-axis. If whenever x comma y is on the graph, x comma negative y is also on the graph. Graph is symmetric with respect to the origin if whenever x, y is on the graph, negative x, negative y is also on the graph. Let's draw some pictures for each one of these. So let's start off with symmetric with respect to y-axis. So what this says is whenever x, y is on the graph, here's a point x comma y, negative x comma y also needs to be on the graph. So we have that over there. If we have this point, we are reflecting things over the y-axis, and so maybe this is what? This is an example of a function that is symmetric with respect to the y-axis. And graph is symmetric with respect to the x-axis. Let's do this one. Okay, so whenever x comma y is on the graph, x comma negative y is also on the graph. So if we have this point here, we need to x comma y. We also need to draw x comma negative y, x comma y, x comma negative y, x comma y, x comma negative y. We're reflecting things over the x-axis. So this graph would be symmetric with respect to the x-axis. And then finally, a graph is symmetric with respect to the origin if whenever x comma y is on the graph, negative x, negative y is also on the graph. Symmetric with respect to origin. Okay, so what would this one look like? So if here's our point x comma y, negative x, negative y would need to be here. If here's our point x comma y, negative x, negative y, x comma y, negative x, negative y here. And so this would be an example of a graph that is symmetric with respect to the origin. It has some kind of like radial symmetry. If you could pick up the graph of the function, rotate it 180 degrees, you would get this graph again. Okay, so so here's examples of these three symmetries here. Let me ask this: are these all functions? And so the thing that you should realize here is that this one does not give you a function, because whenever you have if x comma y is on the graph, x comma negative y is on the graph. And as long as y isn't always 0, that will give you two values of two outputs for a single x input. And so that's not allowed for a function. So this one can't be a function. These two could be functions here. And so this leads us into this next definition here. For symmetry and functions, an even function f has the property that f of negative x is equal to f of x for all x in its domain. Odd function f has the property that f of negative x equal to negative f of x for all x in its domain. This one is saying, the even function is saying the graph is symmetric with respect to the y-axis. And this one is saying the graph is symmetric with respect to the origin. So here is a function that is, this one is an even function, this one is an odd function. Symmetric with respect to the y-axis, symmetric with respect to the origin. Now you might be wondering, why are we using even and odd? Even and odd are adjectives that we usually use to describe numbers. 4 is an even number, 7 is an odd number. And so as it turns out, there's a good reason for that. So let's consider f of x is equal to x to the fourth. So for both even and odd functions, the definition is replace x with negative x and see what happens here. So we do f of negative x. F of negative x would be negative x to the fourth. It would be negative 1 to the fourth x to the fourth. We can rewrite in that way. Negative 1 to the fourth is in general, x to the 1, sorry, minus 1 to the fourth is just 1. 1 times x to the fourth is just x to the fourth, which is f of x. So here we see that f of negative x is equal to f of x. And here, that's the definition of an even function. This is even. Well, let's also think about, I said 7 was an odd number. What about g of x is equal to x to the 7th? Well, g of negative x is equal to negative x to the 7th. We can rewrite this as negative 1 to the 7th times x to the 7th. Negative 1 to the 7th is negative 1 times x to the 7th. And here we see that this is equal to negative g of x. So g of negative x is negative g of x. That's part of the definition of an odd function. So this is an odd function. And this is not, these two examples are not accidents here. So f of x is equal to x to the 2n. I'm making the exponent here even, is an even function. And g of x is equal to x to the 2n plus 1, where the exponent here is an odd number. This is an odd function. Okay, so so even powers of x and odd powers of x are great examples here of even and odd functions. So let's end this video with this example here. Let's discuss symmetry of these three functions here. And so when I say symmetry, basically, are they even, are they odd, are they neither? Not all functions will be either even or odd. This kind of special things here. So let us do, well, okay, f of negative x is going to be negative x to the fourth minus 2 times negative x squared minus 20. Negative x to the fourth is just x to the fourth. Negative x squared is x squared minus 20. So we're back to f of x. So this is an even function. And even functions are symmetric with respect to y-axis. And let me just point out here that all of the powers of x that are appearing in f of x are even powers. X to the fourth, x squared, and negative 20, we can think of negative 20 times x to the 0. X to the 0, of course, is 1. So 4, 2, 0, those are all even powers. As for g of x here, so g of negative x will be negative x cubed minus 3 times negative x plus 1. Negative x cubed will be negative x cubed. Negative 3 times negative x is plus 3x plus 1. And so let's just observe here. This looks like, if we factor out a negative sign, this looks like that this is, okay, so negative x cubed minus 3x minus 1. And note that this isn't negative g of x because the plus 1 has become a minus 1. So this is not equal to negative g of x. There's no symmetry. This is not even and not odd. So, you know, any positive number, any positive integer, I should say, must be either even or odd. But functions in general, you know, don't have to be, you know, either even or odd. This one is neither even nor odd. And again, let me just kind of make the point here. This 1 is really 1 times x to the 0. The exponents here are 3, 1, and 0. 2 of them are odd, 1 of them are even. It's not all odd or all even, so we shouldn't expect there to be symmetry. Finally, h of x is 1 over x cubed minus x. And so let's do this one. H of negative x is 1 over negative x cubed minus negative x. And so this ends up as 1 over negative x cubed plus x. We can factor out a negative sign from the denominator to write this as negative 1 over x cubed minus x and realize, okay, this is the negative of h of x. So because h of negative x is equal to negative h of x, this is an odd function, and it's symmetric with respect to the x-axis. Or sorry, not the x-axis, the origin. Okay, so that's a little introduction here to symmetry in graphs and symmetry in functions.